Hello all. I'm really excited and happy to be here today. And thank you. I thank you all online audience for coming to our presentation. Our topic is model-based testing approach for financial technology platforms and industrial implementation. We represent Exactpro team, and we will speak about how model-based testing is implemented for black box testing of complex systems, financial systems that underpin financial market. But let's first bring up some basic terminology. The previous speakers, they dwelled a lot on testing. I think it's clear for all that the main purpose of testing is to demonstrate that system under test are fit for purpose and to detect defects. And the definition of model-based testing given by ISTQB glossary is testing based on or involving models. But when we think of models, we need to outline the most significant features a model should possess. So according to Herbert Stachowak, a model needs to possess three main features. The first one is model is based on the original. The second, model only reflects a relevant selection of the original properties. And a model needs to be usable in place of the original with respect to some purpose. If we query model-based testing, we see about 8,000 results. And if we listen to today's earlier presentation, they see that this is a very broad area of research. MBT is being increasingly adopted to automate testing and bring intelligence to quality assurance. Let's just give some basic outlines. The notion of model-based testing, it dates back to 70s, and it was called double specification testing. And since then, MBT has received much attention, and when compared, and it was discovered that when compared to traditional testing approaches, MBT indeed brings increases both quality and efficiency of testing in comparison with so-called manual execution. But the MBT approaches vary significantly, and there exist myriads of technical proposals, and in last 2 decades, different variants of surveys started to appear, which try to classify and to give some structure to the existing experience in the area. Here on the slide, I listed here I found this two works which we will use as a framework to describe our approach, and these are 2 most cited surveys. Another work that is mentioned here is by Mokt, Safi and al. This is the most recent survey on model-based testing, model-based test case generation, and model-based test case prioritization. What is interesting about this survey that initially they selected about 7,000 approaches. Then they narrowed their search to about 300 approaches, and only 1/3 of all articles they described real-world case studies, that is originating in the history. And the authors of the research called the other 2/3, they were toy case studies, that is not fulfilling real-world requirements. And of all 300 reports, researches, only 1/10, that is 30, were real case studies that were open source and available. So the objective of our today talk is to speak about how model-based testing is implemented at Exactpro and how models integrated into H2 are used for the black box testing of financial ecosystems. Models themselves are proprietary since they contain customer-specific logic, but TH2 framework in which models are integrated is open source and available, and that's why we think that this research will be helpful for practitioners. So it's not the purpose of today's presentation to speak about TH2 in detail, but if you're interested on Exactpro site, there is a link to GitHub, so where you can see documentation and also the code itself. So today we'll speak about characteristics of Exactpro's MBT approach, directions of future developments, and also about assessment of the industrial experience with MBT outlined through analysis of survey responses. But I also would like to engage you as a public in these surveys. Andrei, could you please send all three questions, all three surveys to YouTube chat? So I'm asking you right now to validate three statements and say whether you agree or disagree with them. And then by the end of our today's presentation, we'll compare the responses with ones given by the Exactpro testers. Right now, you're welcome to respond while we are speaking, and only by the end. At the end, we will review your responses, and thank you for your participation. Now I'm passing the word to my colleague, Levan. So Levan, you're welcome. Yeah, Andrei, could you please bring back the presentation, and we'll look at the results of survey later.
Only I can't hear Levan or everyone else.
I think
I can hear you.
Apologies for some difficulties. Yeah, so thank you for your responses. Yeah, that's the third. Andrei is sending right now the survey to you. And okay. Thank you. So while we, okay, I see my calling has.
Can you hear me now?
Yeah,
Yeah,
perfectly.
right now.
Sorry. I'll continue. So we use the taxonomy of model-based testing approaches, which was introduced by Utting and his colleagues. And as Luba mentioned, it is a paper which has highest citation rate on Google Scholar. And this taxonomy classifies models in 6 dimensions, differentiating between various model specifications, execution methods, and test generation techniques. You can see these dimensions here on the screen. And the first dimension is the scope of the model. So we have 2 different types of scopes, input only and input output. Input-only models can only generate input scenarios, while input-output models can also generate expected results for these scenarios. From these two categories, we classified our model as input-output. However, input generation in our model is very limited, so it would be more accurate to classify it as output only. The main part of our model is a test oracle, which is written in Python, and it can predict system responses for specified user actions. As the code is not written in a formal language, it cannot be used for generating scenarios. So users write scenarios manually while using combinatorial algorithms to generate input data. Next, I will move to second dimension, which is characteristics. Our model is untimed, deterministic, and discrete. I will explain now what this means. So timed models are mainly required for real-time systems where the exact timing of events is necessary. Our model is untimed. It only tests the functionality of the system under test. The timing issues are checked by the non-functional team. Also, the model sends all requests sequentially, and each new request is sent after we receive the response for previous request. And this avoids any non-determinism that may happen because of concurrency, and the model can predict any behavior in advance. So our model is deterministic. Lastly, our models and systems that we test are of discrete event type, as changes only happen at discrete steps. This is as opposed to continuous systems where some value may be changing slowly over time. This doesn't happen in exchanges. Next, we move to paradigm. Unfortunately, we couldn't classify our model based on the paradigms in the paper. As I said before, our model doesn't use a formal notation for describing the exchange logic, and instead users come up with scenarios and use the model just as an oracle. So this paradigm is not relevant to our model. But you can see what kind of paradigms there exist. We're currently researching using pre-post notations and transition-based models. But at the moment, we just use our model as an oracle. And next, we have test selection criteria. So this concerns how the model chooses test cases from the input space. In the screenshot, you can see an example of how users can specify input actions for the model. We use test case specifications, and also we use combinatorial algorithms that generate input data. And they are used to cover various different order configurations. So this is a part that is automated. And for test generation, we use a bunch of technologies. So we have a pairwise testing tool, which was developed in-house, and it also includes a constraint solver. So this tool is used to get the necessary coverage while reducing the number of test cases. And by specifying some constraints, users can make sure that only valid test data is generated. And for parameters that shouldn't affect the outcome, users can also use random generation. Aside from combinatorial methods, we also created a symbolic execution tool that can generate input data based on some specified logic. For example, we can find which order values will lead to that order being accepted or rejected. So it helps testers to come up with some valid input data for a particular test case. And the last dimension concerns how the tests are executed. We have offline and online execution. With offline execution, tests are generated strictly before they are run. We used such an approach in the past, but recently transitioned to online execution. With online execution, the model is directly connected to the test execution framework using TH2, and it can execute actions against the system and checks the observed responses. And this considerably speeds up the testing process, because with offline execution, testers would need to first generate an intermediate file containing a test script and then execute it against the system using a separate tool. So it was very time consuming. And with that, the classification is finished. And just to repeat all of it, I will go through it again. So our scope is input-output. Our model is untimed, deterministic, and discrete. We couldn't classify our model according to a paradigm. And for test selection, we use data coverage, test case specifications written by users, and we use 3 technologies: random generation, symbolic execution, and constraint solving. And lastly, our model uses online execution. Next, Tiniko will continue and talk about a different classification of our model.
Hello. Levan mentioned the classification by the taxonomy, so we decided to kind of choose another classification as well, which is suggested by DS Neto and the co-authors. For the first criterion, we have the software domain, which describes the type of the systems model-based testing can be applied to. Currently, our models are employed in testing of the trading platforms, which are large-scale, time-critical, complex infrastructures, and maybe in future perspective, the models might be applied to other types of systems which are associated with global financial market. Next criterion is test level, which indicates what types of testing are done by the models. In our case, these are functional and regression system testing, and I will explain what this means. Functional testing is process when the QAs determine if the piece of software is acting correctly and meeting the requirements or not. And regression testing means if the new release or new functionality affected the already existing functionalities or not. Automation level is basically the proportion of automated steps and non-automated steps. Our models tend to be fully automated. However, we have manual steps, which are, for example, testing data input or creating scenarios, which are done by the QAs. The next criterion is supporting tools. In our case, we do not use any external tools except for Exactpro's own tool, TH2, and the models are written in Python programming languages. Other than those, we do not use any external supporting tools. Next one is test coverage criteria. We are doing black box testing, so the data flow and control flow strategies are not applicable for these types of testing. So it still remains a question, so how we can measure test coverage for such complex systems as the financial markets are. Models need to be correct and accurately generate expected results. This is why models are continuously checked at the development stage to make sure that they meet the specifications as perfectly as possible. Next one is cost and complexity, which will be later discussed by Luba in more details. But at the stage of functional testing, at early stage of testing, model-based testing approach can be resource-consuming and time-consuming, but later in testing, in the long run, they are quite beneficial. This is how our models work right now at the moment. but we have future plans, and I will discuss them right now. Currently, our models are referred as active models. This means that after model is executed, it goes through TH2 ACT services where messages are sent. Then in TH2 codec services where internal messages are validated. Then TH2 connects to the system under test, and the expected results from the model and actual results from the system are validated in TH2. Our plan for future is to create a passive model which will be directly connected to TH2 and the system under test, but users will not be able to send messages via model directly, and the model will have a role of passive listener. Here we have the other plans for models. First one is external exchange stub. For testing smart road functionality, we need to stimulate the external exchange. External exchange stub means that model will serve as a smart stub, which will automatically provide the external exchange response based on the incoming messages. Another plan is interactive model, which means that testers will be able to connect to the user interface directly and send required messages to the system. And interactive models will kind of help us to widen our scopes of testing and will help us with exploratory and smoke testing. The aim of generic model is to make the models reusable. It will enable us to adjust the model in a better way to a new client. Generic model will include the basic functionalities which are present in all of the exchanges. Model-based testing approach definitely brings benefits, but they do not come without challenges. And Luba now will talk about challenges and solutions related to the model-based testing.
Thank you very much, Tiniko. So naturally, when introducing MBT into the real-life testing process, some challenges were met, and these challenges are well described in the work by Jan Palesker, industrial strength model-based testing, state-of-the-art and current challenges. And these statements were given to you in the YouTube questionnaire to see whether you agree with them or not. But let me first go through each of the challenge and speak how we cope with them in Exactpro and mitigate the relevant risk. So the first challenge is if complex models have to be completed before testing start, this induces an acceptable delay for the proper test execution. This is cope through processes in Exactpro. At the beginning of the testing project start, all stakeholders, the developers team assess the functionalities and it's decided together with the stakeholders which functionalities should be automated using model at a certain period of time, and models are developed iteratively, and that helps mitigating this risk. So throughout the whole project cycle, model-based automation is accelerating, let's say so. The second challenge is for complex system under test, like system of systems, test models need to abstract from a large amount of detail because otherwise the resulting test model would become unmanageable. We do agree with this challenge, and we faced it. We cope with it by having a system of models. So each system covers a separate functionality, but it's still for us an area for future research, how to make our models clearer and more transparent to testers. And the third challenge is the required skills for test engineers writing models are significantly higher than for test engineers writing sequential test procedures. We do agree, but at the same time, previously, every test engineer had to indicate expected result in each particular automated test scenario, and thus test oracle was spread across all the library, and if there were any changes in test oracle, it was pretty hard to update all automated library. Currently, with the models introduced, test oracle is centralized and developer team owns it, and it's easier to adjust to changes in functionality in this way. And the development team who deals with models is actually smaller than test team. So now let's look at the results of the survey which you answered. Andrei, could you please share the results of the survey that we gave? Yeah, so the first challenge about project schedule. So we see here that the majority of participants strongly agree, 38%. Others, they kind of distributed across the scale. So let's look at the second chart. Again, 50% are strongly, I think these challenges faced a lot in industry, and I do share partially this feeling. So, and the next one, please. Okay, so 43% of respondents strongly agree with this challenge. Yes, every practitioner that would implement MBT indeed will face these challenges. Let's switch to the presentation and see how Exactpro testers responded to the similar survey. So our audience was about 130 people of testers having experience from 1 to 20 years, and they see that the results are different, although on all charts respondents tend to agree with those challenges, but I perceive that only the second challenge, only for the second challenge, all respondents unanimously agreed with the challenge, that is that models need to abstract from a large amount of details, and looking at two other charts regarding project schedule and skills for test engineers, I see that these challenges are quite mitigated to some extent, as I see by the responses. So to summarize, model-based testing is a powerful tool, but model should be fit for purpose, and models should be sophisticated enough to address the complexity of the system under test. So in this presentation, we described how we applied model-based testing to the black box testing of the complex financial infrastructures. Thank you for your attention, and we will be glad to answer your questions. We have Ivan additional here, who is heading one of our models development team, who will help answer the questions.